יאללה. זה פולינום מינימלי. טוב, פולינום מחלק את הפולינום אפילו, פולינום מתקדם. The polynomial of is this, which is the degree of right fundamental of the matrix. Monic steady coefficient, the coefficient that is then coefficient is 1. It is the polynomial of the least degree that when the matrix is degree results in zero matrix. But then the polynomial of A, B, P, T equals this. By definition, A equals 0, which means okay, so it means that when we incorporate the matrix into the polynomial, we get 0. This by definition, it also happens characteristic polynomial. Let's find a polynomial QP such that QCA equals 0. We can use the conjugation n equals 1 divided by CCA. You can sub it into the equation. But why this is true? It's show us the form of the polynomial that ambulates sleeping. אם ההפכה אז קיימת פולינומיה קטנה או שווה לכינוס אחד, כך ש... מה? אם תהיה הפיכה אז קיים פולינומיה אחד שווה אם x פולינומיה תהיה הפיכה אז אם x פולינומיה תהיה אז קיים פולינומיה כינוס אחד. הנה ההפיכה, אז יש פולינום בדרגה קטנה או שווה לכינוס אחד כך שההופכית שלו תהיה equals variable from px degree let n equal to 1 such that the inverse of a equals what is substitute to a determine a matrix vector if and only if the constant term its mean polynomial is not zero. In our case, this means a is zero, is f is zero. Let's see why. If a is zero, if a is zero, going to equilibrium becomes the factor out this which contradicts that therefore if it is it must be that זה מעניין, מעניין. אם A0 שווה 0, אז לא יכול להיות שהיא הפיכה, כי אם היא הפיכה, יש פה יותר קטן של 0, זה ייתכן. which I talk of later. Constant term, you can know is no zero. That's interesting. Okay, so what I want to talk about is the very last fact for the and the matrix. And you can see the theory of linear algebra that says that if a variable, if the constant term in the polynomial is not zero, remember that the polynomial with the minimal degree that annihilates the matrix if you substitute the matrix in the polynomial. So it says that if we have a matrix, it must be that the constant term in the polynomial is not zero. Let's see what works. Just what we're going to do is take into the constant on the polynomial. Let's look how it looks like. This is general form. Okay, and this is a zero constant. We say that if a is a variable, it must be that this is not zero, not zero constant. Let's see one, because if a0 is zero, you can look at the equation like this, right? Because the constant variable is zero. So it's here. If so, you can take out a, right? And you get to this equation. But if you get this equation, if a is invertible, which should not be because a0 is zero, we said that if the constant term in the polynomial is zero, it must be that it is not invertible. A is invertible only if this is zero. Now, if we assume we are wrong and a0 is zero and the matrix is invertible, we will get to if a0 is zero, again, we can look at in this case, we substitute a, and remember that the matrix always calculates its. Now take out a, you get this one. Now, if a is invertible, you can just take the inverse, left side inverse, both sides, and get to this one. And what did you get here? You get a polynomial of degree k minus 1, which is less than the degree of the minimum polynomial, which what it does, he annihilates the matrix, which should not happen because minimum polynomial by definition is the minimal degree polynomial that annihilates the matrix. So we got here that if we have a constant term which is zero and we assume that the matrix is invertible, we get to a lesser degree than the minimum polynomial that annihilates the matrix, which is a contradiction from the definition of minimum polynomial. Therefore, we conclude that if the constant term in the polynomial is zero, the matrix cannot be invertible. And that's it. Nice. Proof. If the constant term in minimum polynomial is zero, the matrix is not invertible. So I can use the minimal polynomial in the case it's invertible to find the inverse matrix. Quite nice. This is a very nice result. You can use the minimal polynomial to find the inverse for invertible matrix. And the polynomial that will be used is 1 degree less than the minimal polynomial, and this is what you see right over here. We have a formula for this, and we can derive it. Then we have found that a minus 1 the inverse equals pa. The degree of this polynomial is k minus 1. This fits the condition that p is less than k minus 1. Okay, the second step. That's very nice. Let's call it finding formula for inverse vertical matrix. Okay, so the idea now is to show you for invertible matrix, let's call it A, how we can find the formula for the inverse using the input. Namely, we see that in the end we'll get to this. The inverse of a matrix equals minus 1 divided by a0, which is a constant in the minimum polynomial, times this. And this is a formula for the inverse, and this is derived from the minimal polynomial. Let's see how it goes. We start with the minimal polynomial of the matrix, which we have it, calculated with the values, and this is the and we assume it is invertible. Because invertible polynomial, the a0 is constant and is not. Here you can see here that y that the matrix the a0 constant is not zero. So assume this is not zero. Okay, so we can take this everything else and take it to the other side. We get this one. Now we know that a is invertible. It must be, otherwise it won't work. So if so, I can take a out and take the inverse from the left side from each side of the equation. We'll get to this, right? Now I can just annihilate this a, and we are left with a, an equation of k minus 1, which is exactly 1 degree below the degree for the minimum polynomial, which is k in our case, and we are left with this. So you can, I want to get formula for inverse of a minus 1. So take a0 to the other side, and you get this, and here we are. We started from the equation, and here we got to form the equation that tells you exactly what is the a minus 1 inverse of matrix. Of course, it doesn't seem very nice to calculate all those powers for the matrix, but it's very neat to see this derivation connecting limit of the inverse, the matrix, and then equation to the inverse. So this is very nice. This is how we can use to derive an equation for the inverse of the matrix. Thank you very much. And that's which is equivalent to saying it's been written as a polynomial in value of degree at most. Okay, so let's continue the matrix. This is between polynomial A and the inverse. If it exists, it's also polynomial A. So it's a harmonic polynomial. It's going to be that thing is working as okay, that was very nice. The best understatement from one. Good, nice. Okay, next question, please. You are getting it. Okay, here it is. Let's go down, go down, go down. Now this. Meanwhile, let's look at this one. So we have transfer from B to B, and then we take the square root into y. So t equals I minus I. Maybe in the what metrics? Oh, we don't see what it not equal to here. But if we take a matrix, let's do it. hmm, If we take a matrix like this, mhm, let's do it like 0, 1, then 0, 1, 0, and 0, 0, 1. Okay, let's assume that I take this matrix. let's see what happens. Okay, what happens when you take this matrix, take this matrix, take it to power two. Hmm. Okay, it's not what I thought it would be. Yes, this is not. Mhm. That's an interesting solution. Okay, look. So, if I take the matrix you showed, I get this one. So, so let's see. Oh, nice. Oh, of course, I can take something like a matrix like 1, 0, 0, 0, minus 1, 0, and 0, 0, minus 1. And by that, I will get still t squared equals I. Let's make sure. Take it to the power of 2. Because, of course, the diagonal matrix taken to the power is taken to the power of its diagonals. So we get this versus diagonal matrix. Very nice solution. So we can Okay, let's try to make a video about it. Okay, so the goal now is to see what are the eigenvalues and which matrices can prove that say the fact that if you take it to the power of 2, it equals I. What can bring into this equation? Which matrices, which transformations? So let's look on this and let's generate. You can write it as well like this, right? Now you can manipulate it such that you know that this polynomial annihilates t, right? Because if you incorporate t here, you'll get to this equation. So you know that this polynomial annihilates t. If so, we have some options for the polynomial. You can also write this polynomial like this. And now we have three options for the minimum polynomial. It can be 10. Remember, remember that the minimum polynomial is the mean the weak polynomial that annihilates the matrix or the transformation. So it can be human. This is not just we don't know if this is a or not. Not must contain all the values. So it can be this one minimal polynomial. So we get this. It means that the eigenvalue of t is one. It can be this. So we get this equation. So the eigenvalue of t will be minus one, or it can be this one. Then we'll have t with eigenvalues 1 and minus 1. For each one of them, you can understand what t is. If you incorporate t right over here, you get t equals I. If you incorporate t right over here, you get t equals minus I. If you incorporate t here, you can get t squared minus I equals 1. But what you can know is that the eigenvalues of 1 and minus 1 can be an options for the eigenvalues are 1 minus 1 over 1 and minus 1. So T can be the identity polynomial, the identity matrix, minus the identity matrix, but also things like this. If you take it at square, to square a diagonal matrix, you just take the diagonal terms and raise it to the power of 2. So if you take this t and raise it to the power of 2, you will get again the identity matrix. So if t squared equals I, it doesn't mean that t might only be I with minus 1. It also means that t equals other matrices with other values only present. We need to say if it's true or not. If A is this matrix, then A annihilates the polynomial t to the power of 6 times. This is a upper triangle matrix. You know that So we can conclude that the only given value of A is 0. So and it's 1, 2, 3, 4, 5, 6 degrees. So it only is 3 to the power of 6. This is the characteristic. And this is the characteristic. So I understood it to the power of 6, but where the minus 2 came. If I have a characteristic polynomial of naught, let's try it out. If I have a characteristic polynomial of t to the power of 6, can it be that t to the power of 6 minus t annihilates can be confirmed state that active square matrices will also be this equation that is polynomial and then P is this matrix. Instead, using polynomial t A divides each of these polynomials into sequence molecular just polynomial is t. So yes, it's possible. The matrix is equal. Uh, no, I don't think this is true. I really don't think that this is true. I think this is not true. So we need to remember that it's not a zero matrix. It's not a matrix. It's true. It's not. Okay, so let's continue. Here it is. Chartist polynomial is to the power of 6. So we will conclude probably that no. Okay, it's not a matrix. It's zero. Let's exercise. Very nice exercise. Do that. Okay. That's very nice. And like asking, can I have a polynomial that animates the matrix for a nilpotent matrix, which is not how they call how they call it. X to the power of 6. Okay, that's a very interesting question. Okay, so the idea of the exercise now is to try to answer the question, if I have a nilpotent matrix and we see that this is a nilpotent matrix in a second, can I have a polynomial which is not a monomial and not of something like 10 of something? I still can things like this, for example, annihilates a nilpotent matrix. This is the question. Or always the only polynomials that will annihilate a nilpotent matrix will just normal. Now, let's see why this matrix is. And remember that a matrix with only eigenvalues of zeros is a nilpotent matrix. So look on this matrix. This is the upper triangular matrix, and all the values on the diagonal are zero. Remember that for this matrix, the, the eigenvalues are the values on the diagonal. So this is zeros. This matrix is only zero eigenvalues. So this is a nilpotent matrix by definition. And for nilpotent matrix, there is a nilpotent index, namely for some power, it will finally get to zero. So the question is, can it be that, for example, polynomial like this will annihilate this matrix? And we will see why it can be. And if you plug in nilpotent matrix to this, and you assume that it can be zero, so what you get is the equation a compared 6 minus a equals 0. Now, this is a nilpotent matrix, so a to the power of 6 will be 0 by itself. So 0 minus a equals 0, right? You get something like this. Therefore, you get that a equals 0, but we're not coming from the 0 matrix. So unless the matrix is the 0 matrix, which is also quite important in the empty sense. So if the matrix is not a 0 matrix, you see that I get to a contradiction if I assume that this polynomial annulates this, because this is of course not the zero matrix. But if I assume that this polynomial annulates the matrix, I get to a equals 0, which is false. So the assumption that this polynomial t to the power of 6 minus t annulates the matrix is not true. So this was just an example on why a nilpotent matrix cannot be another polynomial except for monomials to the power of something that annihilates it, because we get to contradictions. And that's it. But this is not totally true. So let's just erase this. Okay, this is not totally true because you can get another not numbers that emulates metrics, for example, this. So it really hundreds, but the minimal group must be no. So what's the wrong with this explanation? So erase this one. Okay, let's keep going to the next. Now this. Okay, let's see. Oops. Wait. Can you hear me when I speak? I think yes. Oops. This was very loud. For every matrix n above F which cannot be diagonalized, there is a polynomial above F for a degree less than or equal to n minus 1 such that pa to the power of 2 equal 0. We need to read it. The core statement is, for any n-to-n matrix over a field F that is not diagonalizable over, there exists a non-zero polynomial with a degree less than or equal to n minus 1 such that if I take to the power of 2 the polynomial when I substitute a, it equals to 0. What the hell is this question? Not diagonalizable. Whoa, what a question. Wait, matrix with a characteristic polynomial like this means 2 to the power of 2 won't be diagonalizable. Oh, no, minimal polynomial. A matrix polynomial is not diagonalizable. No, it's because we have a Jordan form, which is a Jordan block of size 2, so there is an element that is not 0 on the supradiagonal, so it cannot be diagonalizable. That's why when we have a minimal polynomial with a repeated root, it cannot be that the matrix is invariable. Very nice. Very nice. It is an irreducible factor of the Bulgarian one. This can only happen if the field is not algebraic closed like the field of complex numbers is algebraically closed. This means any polynomial with complex coefficients can be factored completely in a linear factor. Therefore, the only reason a matrix not be diagonal is if its minimal polynomial has repeated roots. So, if it's not diagonal, the polynomial must be of the form where lambda is an eigenvalue, the exponent, and gt is some other polynomial such that g lambda not equal 0. Now, let's construct the required polynomial pt. Let's define. Okay, let's check the properties of P. Is P non-zero? Yes, its degree is, since a minimal polynomial always has a degree of at least 1, P is not zero. Is the degree of that less than or equal to n1? Degree of the polynomial is always less than or equal to 1, therefore degree the condition holds. Is P, let's assume steady into P. Now let's query it. By definition of minimal polynomial, we know that. So, since k equal to, this means that is a factor of m. Specifically, because matrix polynomials in the same matrix commute, we can rewrite our expression since we have I don't really understand why. I don't see why this is true. I don't really see why. Let's try to ask it. If the minimal polynomial of a matrix is can I conclude that? Can I conclude that Not necessarily, I just thought. So I don't see why it says that. Okay, got it. Okay, maybe we will finish for now. I think we will. Okay, so the minimal polynomial of the matrix this is of the degree 2 the most. I think this is not true because the minimal polynomial must have every eigenvalue, therefore its degree must be 3. For a diagonal 22778, the minimal polynomial is this. I think this is true because the minimal polynomial in order to the matrix to be a diagonalizable matrix, and of course a diagonal matrix is diagonalizable by itself, so the minimal polynomial should not have repeated roots but should include all the eigenvalues, and the eigenvalues of a diagonal matrix is the values on the diagonal 2, 7, and 8. So I think, yeah, this is the minimal polynomial. It's maybe not the characteristic polynomial, and it's not, but it is the minimal polynomial, and it cannot be anything else. So this is true, and this is false, I think. Conclusion, false. Conclusion, true. Great. So we got it. Okay. Those are the eigenvalues. Of course, this is diagonal matrix. Characteristic polynomial is this. And the minimal polynomial must divide the characteristic polynomial. Every eigenvalue must be root. The minimum polynomial is this, is of degree 3, so it cannot be of degree 2. So, yes, this is false, as I said. The same reason. Statement 2. I think the statement is true because in order to be diagonalizable, it must be that there are no repeated roots, and per definition for the minimal polynomial, it must include all the eigenvalues and includes it. So I think this is true. So you can see right over here, the eigenvalues are those. For each, the minimal polynomial is this. And yeah. So this was quite an okay question. Okay, so linear factors. So you can say the minimum polynomial for diagonal matrix. This will be nice. So I can make from this a serotonin. Let's just see. Okay. Okay, so the idea is to see what is the minimal polynomial, what is the idea of the minimal polynomial of a diagonal matrix. Now, remember that the minimal polynomial of a matrix contains all of its eigenvalues, and in order for a matrix to be a diagonalizable, and remember that diagonal matrix by definition is diagonalizable because you can diagonalize it with the identity matrix, and it's diagonal by itself, so this is diagonalizable because it's diagonal matrix. So the minimal polynomial of diagonalizable matrix must divide into distinct linear terms. So in the complex numbers, it always can be divided into distinct linear terms, but it also must into linear terms, but they also must be distinct, namely no repeated roots in the minimal polynomial in order for the matrix to be diagonalizable. So divide into linear terms, and then the linear terms should be distinct, namely linear terms and no repeated roots in the minimal polynomial in order for a matrix to be diagonalizable. So in the complex numbers, remember that every polynomial can be divided into linear terms, but it may be that there may be repeated roots. So let's, for example, look on this matrix for an example for a diagonal matrix. What is the minimal polynomial just by looking at the matrix? Can you know that? Of course you can. This is a diagonal matrix, so it's diagonalizable, but by that it's diagonal, as we said. So the eigenvalues of the diagonal matrix is on the diagonal, so it's 2, 7, and 8. So the minimum polynomial must contain, for example, t minus 2, t minus 7, and t minus 8. Now, it cannot be repeated, so the minimum polynomial, those are the eigenvalues. The minimum polynomial must be t minus 2, t minus 7, and t minus 8 without any power to any term. This is not the characteristic polynomial. The characteristic polynomial may be with powers to the terms, but in the minimal polynomial must be, in order for the matrix to be diagonalizable, divided into linear terms, as you can see here, multiplication of linear terms, and no repeated roots, namely each term is to the power of only 1, not 2, 3, 4, and etc. So the minimal polynomial of a diagonal matrix must be of this form. You can see t minus eigenvalue 1, t minus eigenvalue 2, t minus eigenvalue 3, and etc. for each eigenvalue, but this is the form of the minimal polynomial for a diagonal matrix because it must be diagonalizable by per definition. And that's it on the minimal polynomial of a diagonal matrix. Okay, let's do some break here.